has to do with, you are English. It has to do with energy and energy change. And we are specifically going to look at exo and endothermic reactions. Sorry. And graphs. Okay, so you must be wake up. Before we get to that, we are going to do two different concepts that you have discussed previously this year, if I'm not mistaken, but we're going to look at them again. The first one there is dissociation energy, and dissociation means to break apart. And the suffix ation, or ation there, the suffix ation refers to the process of. So if we have condensation, the process to condense. If you have elimination, the process to eliminate. Okay, so dissociation means the process or the energy needed for the process of dissociate, to take apart. So dissociation energy, the energy needed for the process to take apart. And there's exactly the definition, the energy required, needed, to break bonds in molecules. The energy needed to break apart, to break bonds. Then we have bonding energy, and that is the energy that is liberated. Really? What is another word for liberated? Say again, I couldn't hear. Did she say walking? To give off, to set free, to release. In 20 minutes, you'll be liberated from this class. Released. Set free. Okay, so liberated means to give off or to set free. So bonding energy is the energy that is given off, liberated, when bonds are formed in molecules. Okay, so bonding energy is not energy required to make a bond. It's the opposite. So if we have this molecule, if I want to break the bonds, it is called bonding energy. And if dissociation energy. And if I form a bond, it is called bonding energy. When I break a bond, I need energy. It's really that difficult to break this bond. So I need energy, the energy needed to break the bond. Now you can see this atom here has a place where a bond can form. It's unhappy. Electrons aren't paired, orbitals aren't filled. So when it forms a bond, it gives off energy. It's more stable now. Okay, right. So if we look here, I think you've seen this before. Eh? Yes? This table. You're just going to look at it again. Calculate the net energy required or liberated in that equation when that reaction happens. Okay, so the previous chapter where we discussed this, we just said this bonding order is 1, so it means the molecules are closer together, and. Now we're actually going to use these values and do calculations. Okay, so if we look here, this is methane that reacts with chlorine gas to form chloromethane, new words for you, and hydrochloric acid. Okay, so they want to know how much energy, because to break these bonds, we need energy. And then when bonds are formed, it gives off energy. So maybe it's equal, and you have 0. Or maybe to break bonds, it requires more energy than it's given off. So it needs more energy. Or maybe when the bonds are formed, it releases more energy than what it needs to break it apart. Are you with me? Okay. So, for example, let's say, I can't decide if it is warmer or cold if the door is open. Is it cold if the door is open? Okay. Let's say, Hope and I, we are in a relationship. Okay? And let's say this relationship is not going super great. So to break up this relationship, it won't need a lot of energy. Yes? So now, let's say it requires 10 joules of energy. Okay? And now I go in a relationship with partner. So when this relationship forms, we're a better match. So when we form, it releases 60 joules of energy. Okay? So it's not that this relationship is 10, so this relationship should be 10. Okay? This relationship didn't work out that well, so it takes about 10 joules of energy to split up, but when this relationship forms, it releases 60 joules of energy. So what is the net change in energy? 50 plus or minus? Minus, because this needed energy plus, it needed energy to break, plus 10, and this gave away 60 energy to when it formed. So it's negative 50. Okay, so same concept here. Now, before we can do that, we must first see the type of bonds. Okay, so you are going to draw the Cooper notations. You have done the Lewis structures. And I've mentioned, before I left, I mentioned Cooper notation. Cooper notation is just that one line. Okay? So if you look at it, we have methane there. And then you have chlorine. And that gives you chloromethane and hydrochloric acid. Do you think you'll be able to draw that? Okay. Yes. What? Chloromethane. Yeah, it's not good. If you inhale it, you'll pass out. Okay, right, so let's see what changed. From here to here, what changed? We saw this bond broke and this bond formed, right? And here, this bond broke to form that one. Okay, so I'm going to highlight 4 things. This and this broke up, and then this and this formed. Okay, so where am I with my questions? Did I start now? Chlorine, let's start with you. To break bonds, what do we call that energy again? Dissociation. So the dissociation energy, I have 1 mole of carbon hydrogen and 1 mole of chlorine. That broke and that broke. If this one also broke up to form, and this two of them also broke up, for example, okay? But let's say this one and this broke, then it would have been 2 mole. Okay, are you with me? Right. But if this was a double bond, then it's not 2 mole, then it's just a double bond. Okay. Let's see. Values. Carbon, hydrogen. To break up carbon, hydrogen there, you need how much energy? 414. Okay. So to break that up, you need 414 energy. If it was 2 mole, then you would have said 2 times 414. Okay? Then chlorine, where's that? Here it is, 243. So this is plus 243. So the net energy needed to split up the bonds is 756 kilojoules per mole. Plus. Okay. If we look at the Retabile, what is the energy given off when bonds form? Bonding energy. So the bonding energy is the energy that is needed, required. Okay, now I'm not going to write out 1 mole, 1 mole. I already explained to you the mole. I'm just going to say we have carbon chloride and hydrogen chloride. If we look at the table, carbon chloride, the energy that is given off, so that is subtract, it's minus 339. And hydrogen and chlorine, there, hydrogen and chlorine is 431. So negative 431. If you add that together, you get negative 770. Okay, so what was the question? The question was the net energy. Some of you still have accounting? Yes? What does net refer to, Khali? The total, when you add and subtract everything together. Okay? So, add and subtract everything. So, when you add everything together, what do you get? So, the net energy is 657 minus 770. And that gives you negative 113 kilojoules per mole. Chop? Okay. So what did you just calculate? You just calculated if a reaction takes place. Does it need more energy or does it give off more energy? Okay, it will always need energy and it will always give off energy, but does it need more or does it give off more? Which one is the bigger one? Okay, are you with me? Okay, so you've calculated the net energy required, and that is called the heat of the reaction. So that which you've just calculated, that E net, is called the heat of the reaction, or the reaction heat. The symbol for that is triangle H. Remember that triangle refers to delta, which means final minus initial. Okay, another name for that is the enthalpy. So if you go to old question papers, it will be called enthalpy. Enthalpy. Okay, so what's the definition there of the net energy or the heat of the reaction? Is the energy absorbed or released or liberated in a chemical reaction. How much at the end was given off or needed? Okay, to calculate that, fancy way, is the energy of the products minus the energy of the reagents or the reactants. And we measure that in kilojoules per mole. How much energy per 1 mole? Okay, then before we can go to the graphs, 3 more things, is you have something called the activation energy. The activation energy. Okay, the definition there is that is the minimum, you must say the word minimum, is the minimum energy needed for a reaction to take place. Okay, so that is the same as the dissociation energy. The energy needed, required for the reaction to take place. Okay, back to my example of me and Hope. To break up this reaction, the potential energy required is 10 joules. Okay, but now let's say Katu has her own and she wants to split this up. She only has to say, give me 1 chocolate, and then I'm jumping. Okay? But now she wants to make sure that this reaction is going to take place. So she doesn't give 1 chocolate, she sends 1 chocolate, a bunch of flowers, and